So, for those of you who don't know me, my name's Clinton Hilliard. I'm the outgoing programs director for Incose Chesapeake. The incoming programs director had some stuff he had to attend to this month, so hopefully he'll be picking things up in February. So we will be at the end of the, stay till the end, because we're going to be raffling off a door prize, and that door prize is going to be this book that Ms. Scalco recommended, Creativity, Problem Solving, and Aesthetics in Engineering. So that sounds like a good topic, so it should be a good prize to win. Feel free to put your questions in the chat box, and I'll leave it to Ms. Scalco to either answer in situ or wait to the end. But definitely feel free to put questions in the chat box. So this evening, we are honored once again to host Miss Aleksandra Scalco. Like I said, last October, she presented to us a talk that took a look at some of the imperatives and needs for cybersecurity relating to control systems. And this time, she'll provide us with, I believe, a look towards potential remediation of those types of vulnerabilities. So Ms. Scalco is a CSEP with Incose, and she's currently an engineer with the Naval Information Warfare Center, Navy. She is a technical manager for mitigations of control systems vulnerabilities. She has authored several articles covering cybersecurity for control systems. From 2012 through 2016, she was an information system security designer and a client advocate with the National Security Agency. Currently, she's pursuing her PhD in systems engineering at the Colorado State University and has also a master's in engineering and systems engineering from Iowa State University. She holds an MBA from the University of Physics and a bachelor's degree from the University of Missouri. Oh, did I say University of Physics? University of Phoenix, sorry, and a bachelor's degree from the University of Missouri as well. Her research interests include cybersecurity of control systems, obviously, digital transformation of cyber physical systems and control systems engineering of cybersecurity capabilities for context-sensitive dynamic classes of critical infrastructure, and multi-concern assurance. Operational technology software-defined networks, and the development of tactics, techniques, and procedures using software orchestration to achieve cybersecurity for control systems. Her awards and honors include membership by invitation of the 7th cohort of the International Council on Systems Engineering, Institute for Technical Leadership, and NSA CSS Crescent Performance Award for Mission Excellence in 2013. I'm going to turn the podium now over to you, Ms. Scalco. Let me stop sharing here.
Thank you, Clinton Hilliard. You're always very gracious. I really appreciate the kind introduction. I'll start my, let's see. Hopefully you can all see the slide there.
Yes.
We're good to go. All right. Thank you very much, Dave Flanagan, President of the Chesapeake Chapter, Clinton Hilliard, for your gracious introduction and support, and the rest of the Chesapeake Chapter. I really appreciate these opportunities to speak with you. So thank you for inviting me to share some aspects of my dissertation research with the Incose Chesapeake Chapter. Aspects of this work are being used in fulfillment of my requirements for a systems engineering PhD at Colorado State University. The views and opinions expressed are my own. They do not necessarily reflect any official policy nor position of any agency or entity of the United States government. A bit about me. Thank you, Clinton. You gave a kind introduction. I was here previously and am absolutely thrilled to come back and share some more thoughts and ideas. The last time we met, I talked about quantifying the cost of control system cybersecurity. Today, I'll share my analytic model and a methodology to measure disagreement in segments of cybersecurity profession as a means of identifying vulnerabilities through statistical uncertainty analysis of Likert semantic differential scales. We know that if people disagree on certainty in the field, that is a source of vulnerability. The cyber attack in the Oldsmar, Florida water treatment facility highlighted the vulnerability of control systems that often use legacy software and hardware. The continued use of old, unsupported operating systems that contain well-known vulnerabilities means that even if control systems are perceived not to be internet-facing, they can still be easy targets. We've already established that there's vulnerability. Can we go further? Are there different types of vulnerability? Measuring disagreement in segments of the cybersecurity profession can identify different types of vulnerability. If we have two entities who disagree entirely on where the system is most vulnerable or uncertain, we have overall vulnerability. So measuring disagreement among professionals can help to resolve transition readiness gaps for new capability acquisition into operations to respond to threat intelligence, align with strategic guidance, drive investment, and help inform budget or resource and funding decisions. Command and control are composed of information management, decision management, and execution management. The variables include a complex system of people, processes, procedures, technology, doctrine, coordinated to realize the mission. The entire system, including the system's role at the time of operation and the environment in which it will operate, can be impacted by any change. So adversaries target critical infrastructure physical systems such as power, water, and facility-related control systems using automated cyber attacks, looking for those change spaces. The DoD operates thousands of networks and millions of computing devices dispersed worldwide that are all vulnerable to attack. In the DoD, JSIDS is the formal process to address capability gaps and define the acquisition and evaluation of criteria for solutions. A significant emphasis of the .mlpfp that you see in the bottom right-hand corner is to support the development of a material solution. The output of the JSIDS analysis defines needed capabilities, guides material development, directs production of capabilities, all in coordination with the joint staff. But the DoD must unambiguously align the entire ecosystem shown in this slide from strategic guidance throughout the .pmlfp process to achieve command and control. Therefore, it becomes worthwhile to understand overall agreement or uncertainty. Alignment of agreement is critical to the Department of Defense when concerned about greater energy security, acquiring or disposing or maintaining installation networks, as well as overseeing occupational health and safety issues. So of course, new complexities are introduced by innovation, new technology, and methodologies. So these complexities also present the opportunity to rethink strategies and new options to ensure that infrastructure is resilient in the face of unknown challenges. In World War II, the loss ratio of enemy aircraft to US aircraft was 14-1. During the first years of the aerial combat in Vietnam, that ratio fell to 2.5-1. Surprising, considering the United States employed sophisticated, high-performance missile-armed fighters. There are many compelling factors, but that ratio indicated problems. For example, there was a lack of professional agreement on whether a pilot needed capability for close aerial combat. The high value of the Phantoms, the F-4 Phantoms, was the ability to destroy enemy planes from 10 miles beyond visual range. Beyond visible range is how the Navy trained F-4 Phantom pilots to fight. Most did not know how to fight any other way. However, doctrine prohibited a pilot from firing beyond visual range. A fighter pilot had to first confirm the target visibility, potentially attributed to the opinion that the enemy would be confronted from a distance using missiles. The falling ratio resulted in creating the Navy Fighter Weapons School, known as Top Gun. After Top Gun and other measures, the Navy's ratio was back to a ratio of 13-1. The vulnerability induced by such misalignment may be greater than the innate system design vulnerability. Measuring disagreement in segments of the cybersecurity profession is used as a means of identifying these vulnerabilities. Disagreement exists among professions due to variances in engineering practice, paradigms, processes, and culture. Understanding the whole picture and what can be done to improve things is a continuous science and engineering challenge. This challenge holds particularly true for systems that control the physical world, such as power systems. Disagreement produces misalignment, leading to vulnerability. It is possible to measure the uncertainty of agreement through the statistical analysis and an analytical model to identify pain points where different stakeholders disagree. The same measure can be walked back to stakeholder sources, beginning with vulnerability assessment to drive better alignment and eventually agreement. It's the disagreement that ends up in vulnerability. In this brief, I described an analytic model and methodology as a new means of assessing uncertainty and interpreting Likert scores to overcome control system cybersecurity vulnerability. A mathematical model and analytical methodology are used to measure the disagreement in the segments of cybersecurity professions to identify those vulnerabilities through statistical uncertainty analysis of Likert semantic differential scales. The model allows us to put the finger on where there may be disagreement, which leads to misalignments and vulnerability, and walk that back through the model from exposure to alignment to agreement. The analytic approach shows correlation to agreement, and then lack of agreement is the vulnerability. A little bit of background. The first publicly known digital weapon targeting equipment and operations that control the physical world was the Stuxnet worm in 2010. Stuxnet specifically targeted industrial software and equipment for uranium enrichment. Since 2010, attacks on control systems have been increasing, creating the need for championing change in cybersecurity of control systems. These are computing devices that control physical world processes. While a typical computer is estimated to have a lifespan of a couple of years and an expectation that updates and software fixes are made frequently, control system devices are different. The lifespans can span up to 30 years or more. These systems rely very frequently on legacy operating systems with very weak resistance against common attack techniques, even as conveniences such as remote access are introduced. HR 1833, introduced in March of 2021, gives greater authority to the Cybersecurity and Infrastructure Security Agency to defend critical systems against cyber attack. That was followed by Executive Order 14028 that removes barriers to sharing threat information to ensure acceleration of incident deterrence, prevention, and response efforts. We further saw in January or earlier last week in 2022, President Biden signed a national security memorandum to improve the cybersecurity as well. All of these start to establish a national security memorandum so that at minimum national security systems employ the same network security measures as those required of federal civilian networks. In 2020, a global pandemic focused on essential critical infrastructure workers as a key infrastructure sectors underwent global transformation. The global COVID-19 pandemic caused many workers to quickly move to online work environments without cybersecurity training, processes, plans, or tools to ensure that fundamental cybersecurity rules followed the remote work transition. The pandemic demonstrated an increased change to the levels of teleworking than previously witnessed. More changes lie ahead as internet connectivity of control systems expands. It's the remote access to operations that increased significantly in 2020. For example, there was an increase reported by the OT and Internet of Things security company Nozomi Networks by some of its customers in extending remote control operations from 9%, or less than 10%, to 60% in less than 3 months. According to Nozomi, ransomware attacks on industrial organizations also increased 500% between 2018 and 2020. Furthermore, the number of incidents increased by 116% between January and May alone of 2021. Predictions are that global ransomware damage costs will exceed $265 billion by 2031. A challenge is that the control system context is different from that of an IT system. As a result, in addition to operating within a diverse environment, OT operators respond to operational anomalies differently than IT users. The system engineering methodology and practice can offer equilibrium to these complex, context-sensitive dynamic classes of control systems. Risk management seeks to select effective control against the most significant risks, the ultimate goal being able to reduce the attack surface to a feasible minimum. But what happens if there's disagreement amongst professionals about how to treat control system cybersecurity? The potential impact of the loss of command and control can be high. The results can be loss of mission, physical injury, or loss of life, economic impact, and social impact. No system can be perfectly secure. The goal is to mitigate the suitable risks in the correct order to achieve an acceptable residual risk level while incurring acceptable costs and operational impacts. First, we have to know what those risks are and the sources of vulnerabilities and agree on how to treat them. Agreement on how to treat vulnerabilities requires that cyber risks are identified and analyzed for an effective strategy to achieve a resilient cybersecurity posture. Darkside ransomware is an example of a malware attack deployed in the oil and gas sector infrastructure sector against the fuel pipeline company, Colonial Pipeline, that was pretty well reported in 2021. The headlines read that the ransomware attack led to one of the nation's biggest fuel pipeline operators to shut down its entire network. However, this was a ransomware attack directed at the business enterprise level of the architecture. The attack was not directed at the lower levels of the architecture to do physical harm. Instead, the shutdown was a call by the organization to prevent any potential for grave damage. However, it can still be seen as an example of how disagreement may lead to misalignment that results in vulnerability. The threat actor compromised the network system with a single compromised password. A compromised password was likely used by an employee of Colonial Pipeline on multiple systems, which eventually enabled the credentials to be obtained by the hacker. Additionally, the threat actor accessed the network system through a virtual private network account that allowed employees to remotely access the company's computer network using the now compromised credentials. A best practice that is known is to protect the network by protecting against remote access or virtual private networks, protecting wireless access points, using strong passwords to protect against unauthorized access to a physical system. But if engineers believe security controls or safeguards to eliminate or reduce the threat or vulnerability are in place, and other personnel, such as technicians, are in misalignment or disagree, then there's a problem. Suppose safety personnel considers access convenience by remote access and shared credentials is valuable. In that case, a misalignment may induce vulnerability to the system that is greater than the system design itself. Preparation is crucial in response. There's no compass for context-sensitive critical infrastructure dynamic classes that's characterized in any meaningful way while best practices, guidance, and standards and policy catch up. Approaches differ by sector, subsector, segment, such as government and commercial sector. We can look to nature for inspiration of ways to solve vulnerability challenges, such as the synchronized schooling behavior of fish that can be used for inspiration. We can also look to literature review. Wolfgang Schwab and Matteo Pujol provided a survey of the state of industrial cybersecurity in 2018. Their findings were that most companies surveyed stated that cybersecurity for control systems is a significant priority. While most thought the company would be a target of a cybersecurity attack in the operational technology space as likely, only 23% were actually compliant with any minimal mandatory industry standards or government guidelines and regulations. Half the participants stated the company did not experience a cyber incident in the previous 12 months, but Schwab and Pujol observed that participants may not have recognized, even if they had, most could not detect an event or much less track them. The data showed that 8% revealed that they did not know, and worrisome 10% did not even measure cybersecurity incidents with control systems. Further, a finding was that IT and OT professionals possess varying goals, processes, tools, and even language. Using Top Gun in the literature review as a benchmark leads to the question, is there a similarity of the uncertainty of agreement by professionals about cyber solutions for control systems? An observation is that if the degree of agreement varies, the capacity to accomplish the assigned control system mission may vary also, affecting command and control over the control system domain. I rephrase my research predictions into two main hypotheses, a null and alternative. The null predicted no actual effect, no relationship between variables, or difference between groups. An alternative hypothesis states the central prediction of an actual effect, the relationship between variables or difference between groups. And then we end the hypothesis testing with the assumption that the null hypothesis is true. Using this procedure, we were able to assess the likelihood or probability of obtaining results under this assumption. My research objective was to measure the uncertainty of agreement about cybersecurity to achieve and maintain command and control over the domain. The null hypothesis is that there is no uncertainty, and my alternate is that professionals' degree of uncertainty of agreement varies. I'll talk about how we did that. An essential part of the research methodology was obtaining institutional review board protocol approval for the study. In 2020, I obtained certification from the Collaborative Institutional Training Initiative under requirements set forth by Colorado State University. Dr. Steve Simsky, a professor of systems engineering at Colorado State University, also who's previously a fellow and VP and director at HP Labs. He directed the research of my advisor and expert in the field. The collection occurred between August 2020 and February of 2021. Questionnaire was developed to sample representative data to make statistical inferences about the population. A mathematical model was created to perform a statistical test of the groups by results by group variance. So I'll present some of the initial findings in the quantitative data section. Depending on the section, respondents were provided questions with anchors on a point scale. Anchors are those descriptive words used on every point of the scale. R-square was used to measure the variance rather than the model's predictive capability. It's also helpful for gaining insights into the relationships among the variables in the data. So R-squared tells us how much of the variance from the mean does our model account for. The values of R-squared vary between 0 and 1. 1 is the highest. It means that the model can explain 100% of the variability of a target variable. If the model accounts for 100% of the variance, or R-squared equals 1, we can say it perfectly explains the observed data points. If the model accounts for 0% of the variance, or R-squared equals 0, we can say that it precisely explains nothing about the observed data points. So we'll get into some of the questions now. A best practice is to start where you are. For me, that meant better understanding the workforce sentiment. We decided to use a Likert scale to measure attitudes and opinions about cybersecurity for control systems. A Likert scale questionnaire makes complex opinions simple to understand. We can all agree that the command and control of cybersecurity for control systems are highly complex, and responses may be complicated. There's no single question that makes someone sure about the cyber domain. Therefore, instead of asking one question, we measure how much professions agree with various statements about cybersecurity with a rating scale. When we combine or average a person's responses, we get a more accurate measure of the degree of certainty of opinions. A Likert scale usually offers one or more questions, a series of answers, and a neutral midpoint. The Likert scale is not always a numbered scale. Instead, it can measure a level of agreement. So for example, participants were asked whether critical assets related to control systems in their organizations had been identified. Response options included yes, no, and a neutral option, I don't know, so that undecided respondents are not forced to give an opinion. We had good responses. Thank some of you on the call here or on this brief, I think participated. We had a total of 187 people who responded, with 100 completing all 203 questions, not counting the one open field offer to contact us, although many did. So thank you for those who contacted us as well. In calculating the mean or averages of the post-questionnaire instrument, I first looked at all the responses, which gave a mean of 126. Then I removed those who only opened the survey and didn't go beyond the consent question, which gives a mean of 145. I removed those who stopped taking the questionnaire after the initial profile questions, which gives a mean of 170. The survey is used as a launch point for the tool. And the survey is used to create an analytical model driving through correlation to assess disagreement, misalignment, and vulnerability. That gives a framework to work backward from that vulnerability to agreement and alignment. The vulnerability induced by misalignment may be greater than the innate system design vulnerability. A numerical value was assigned to each item. So if the Likert scale included responses of yes, no, or I don't know, they were coded yes is 1, no 2, I don't know 3, so that a higher score reflects a higher level of uncertainty for each item. Higher level uncertainty, I don't know, is the 3, right? So after entering the individual scores, the mean was calculated, or the mean score for the whole group for each question. Data in each category was given both a Likert entropy score and a Likert coefficient of variation rank, which is shown in the equations on the slide. If everyone agrees and knows this is where we should start, we're in a pretty good shape. So I'm trying to show where we're not in pretty good shape and where we are in pretty good shape. Calculating the coefficient of variation as the measure of dispersion is helpful when comparing scores with different units of analysis or means, which allows us to understand the disbursement of scores from participant to participant. The percentage coefficient of variation generated is a dimensionless ratio of the standard deviation divided by the mean. The ranking is by questions and overall comparison of ranks. So entropy and coefficient of variation are ranked and summed for a total overall rank of uncertainty that's illustrated in a scatter chart, and I'll show those here shortly. The measures of dispersion of a data set of response relative to the mean are first calculated as the square root of variance by determining each data point deviation to the mean to generate the chart from the survey results. So in other words, the measure of the dispersion of an individual participant responses to the questions is calculated by all participant responses to questions placed in a bin based on the 9 sections of questions described earlier about aspects of multi-concern assurance. So for example, a set of questions might be a block of questions about network systems, infrastructure, incident response, or training and certification. Responses to the set of questions are analyzed by X and Y variables such as occupation, in other words, engineers, computer scientists, and technicians, by employment sector, X and Y variables such as federal, non-federal, commercial sector, or by critical infrastructure sector for the X and Y variables such as transportation, communications, IT. The mean Likert value for a question and the standard deviation of the Likert value is then calculated. So for example, the standard deviation of the response count from all engineers to questions about network systems is calculated for each question. The mean and coefficient of the variation are calculated for each question by all responses by each employment sector, such as engineers. And the same calculation is performed by each sector. Finally, the value of the function y is plotted against x to see if one variable response is fully explained by the other. The test was run viewing variables such as engineering as the y variable and computer scientists as the x variable, and flipped around as engineering is the x variable and computer scientists as the y variable to observe the relationship. So then again, the entropy and the coefficient of the variance were each ranked in the bin for each question. And the ranking scores is from 1 to n, with the maximum domain and range of the chart being 2n assigned to the data. So we'll go on to look at some of the data results. The statistical significance indicates that there is a pattern. So R squared is the strength of the pattern. R squared ranges from 0 to 1, where the value represents the amount of variation in the dependent variable explainable by the variation in the independent variable. And we want to let the data talk. So anything less than a 0.3 is weak. 0.3 up to a 0.5 would be moderate, and 0.7 strong. A scatter plot is used as a tool for analysis to examine the responses by 2 variables such as the engineers and computer scientists, engineers, safety occupations, to show how much the 2 occupational variables correlate by giving a visual sense of the data. The strength of the relationship is established by how close the data points are plotted on a straight line. Data points on a straight line from the origin from a high X and Y values show a positive correlation. Entropy measures the amount of uncertainty or unknown in the data with a visual perception of correlation explained by measuring data related to the X and Y variable pairings and by the amount of space taken on the scatter plot. So the experimental points are plotted and later reviewed to see if there's agreement in relative ranks. In the questionnaire section about network systems, an image of the Purdue model is used to reference a control system network so that the participant can understand multi-concern workforce assurance agreements in the process. So in risk management process, for example, risk reduction is the activity of applying security controls or safeguards to eliminate or reduce the threat or vulnerability. Figure 1 shows engineers' agreement with computer scientists about network systems has an R-squared value of 0.7529, which quantifies the strength of the correlation. An R-squared of 0.7529 means that 76% variation of one variable is entirely explained by the other. However, the agreement of engineers with safety personnel about network system shows no statistically relevant correlation with an R-squared of 0.0003, as shown in figure 2. The same questions participants were asked about network systems when examined by engineers in safety occupations show the question, I have decision authority for which risks are accepted as related to cyber physical systems, shows as points 15 and 28 in figure 1. Another question, our organization uses threat detection capabilities, shows as point 15, 23 in figure 2. Plot 4646 in figure 1 shows responses of the engineer, y coordinate 46, with computer scientists, x coordinate 46, to the question, I have cyber awareness training, which for engineers, y coordinate 46, and safety personnel, x coordinate, is plotted as 1546. So the x coordinate 15 is the total rank sum of the rank entropy and rank code of the safety personnel responding to the question. The y coordinate 46 is the rank sum of the rank entropy and rank code of the engineers' responses to the question. The correlation of agreement between engineers and safety personnel is plotted again as point 15.6. Where the correlation is very poor, these professionals will be at odds, which is worse than not fixing the control system infrastructure. In addition, parts of the organization population trying to improve the infrastructure or the network systems will be competing against each other for the system's functionality and security. In this figure, we see the dependent variables as engineers, and the independent variables are other occupations such as computer scientists or technicians. You can see the engineer and computer scientist agreement about network systems is in the upper left-hand corner. R-squared of 0.75 for engineers and computer scientists is relatively high for the data set, means 75% variation of one variable is entirely explained by the other. It's a big deal to be able to account for 3/4 of what we're examining. This single variable explains 75% of all the uncertainty of agreement without controlling anything else. When we examine the agreement of engineers with technicians about network systems or infrastructure or network systems, as seen in the bottom right, we see an R-squared of less than 4%. That is enormously significant. This one variable cannot explain the variation. So we want to let the data talk and avoid any spurious correlation by connecting variables that may appear causal but are not due to an unseen third factor not apparent in the initial examination. Two variables may be statistically related but not causally related. These two variables falsely appear to be associated with each other. So for example, participants were asked 20 questions about infrastructure, such as question 48, I have access to the physical network topology. Question 49, I have access to the logical network topology. Question 50, with the critical assets related to control systems in our organization have been identified. The variation of engineer and computer scientist and the data and the engineer and technician data shows the uncertainty of agreement about cybersecurity for control systems. OT personnel come into their, or operational personnel come into their field through backgrounds in education in engineering disciplines such as electrical engineering, mechanical engineering, or industrial engineering, in addition to the on-job training. IT personnel come into their field predominantly through computer sciences, vendor-specific or non-vendor specific training and certifications, and on-the-job training. Knowing what the compromises are in a system is a sign of hope. Not knowing what it is and not agreeing on what the state is in a field is a vulnerability, because each group will be complacent in one area and non-complacent in another, and they will be competing. Skills found in OT occupations generally require more extraordinary experience with older technologies than those found in IT enterprises. So I'm saying that if we compete with each other, that leads to vulnerability. We need to come to a common understanding, or we'll not be able to build a system from the ground up that addresses cybersecurity needs and the system's functionality needs, let alone retrofit cybersecurity into a system. If there are A and B components of a system that need to be secured, and if one group thinks system A is in good shape and system B is in terrible condition, and group 2 believes that A is in terrible condition and B is in great shape, the two groups will not only compete with each other, but will also undermine the work done in each of those areas. A common understanding of cybersecurity for control systems is needed. Further, retrofitting IT onto OT is considerable risk because the operational technology systems were designed without knowledge about the future of IT. So retrofitting security is problematic. A better approach is an early collaboration, agreement, and alignment between IT security and operations teams, or SecOps, to enhance security by integrating tools, processes, and technology from the ground up into the system. Currently, standards are still emerging and are voluntarily implemented. Understanding the whole picture and what can be done to improve things is a continuous science and engineering challenge. So we have the surveys. We turn the Likert scores into types of correlations that show uncertainty. Now we know that there's uncertainty that does not correlate across professionals. Where the correlation is very poor, these professionals will be at competing ends. Competition between these professionals it's worrisome. When there's no correlation between professional groups, that is a vulnerability. So when you look at the slide, it shows how engineers, or through any program, how we develop a system or a capability through the life cycle. As you look to the one side where we begin with the needs analysis and concept exploration, you'll see if we're looking at concept exploration and needs analysis for network systems and cybersecurity, that there's a strong correlation between computer scientists and engineers. As we move through the concept definition into advanced development, we see that the correlation between engineers and others starts to become very weak. So industrial management in advanced development, where we have the prototype testing, is weak. As we move into engineering design and development, where we get to field testing, you can see that the R squared for technicians and safety is very weak. So the R squared for safety of the network systems is 0.0003. And that's where the production models are evaluated and at designated test sites. I took a relatively traditional type of survey and used it to gain analytical insights about sets of professionals who work in control systems and cybersecurity. As a result, the analytical process makes it possible to focus on uncertainty in an environment likely to create vulnerability. Here you see a model-based systems engineering, a SysML model, and you can see where there is a correlation of agreement in developing and designing a system. And as we move out towards where the system needs to be fielded and tested, the correlation begins to be weak, which shows that there is uncertainty and there is disagreement, which leads to misalignment, which leads to vulnerability. So these professionals will be at odds. Let's go to a case study and use the use case of protect. In 2021, someone tried to poison the water supply of Oldsmar, Florida. There are approximately 15,000 residents in Oldsmar. The plant's remote access system vulnerability allowed hackers to access the water treatment system. The hacker then attempted to increase the amount of sodium hydroxide, or lye, by a factor of 100 into the water supply. While lye is not harmful in small quantities, it can be toxic in larger volumes. Thankfully, the intrusion was caught, the hack averted, and the unauthorized changes were reverted immediately. A facility supervisor saw the hacker's pointer move across the screen in an attempt to make an unauthorized change to the settings. Serendipity, however, is not security. The intruder was reportedly active for less than 5 minutes. This breach highlights the far more severe impacts that hackers can have on control systems. According to reports, the hacker first appeared in the morning on February 5th. A plant operator noticed remote access to the monitoring and control system of the computer system used for water chemical levels. Initially, the plant operator didn't take any action. They probably didn't understand who might be trying to remotely access the system. Logging into the system was easy to do. However, the city had actually replaced the particular software that was being used 6 months earlier, but the software was never uninstalled from the system. According to FBI findings, a single shared password was used for all the facility computers. No two-factor verification was required, and there were no firewalls in place protecting the controls from the internet. Further, all the computers were running on decades-old discontinued operating systems that had stopped using regular software updates to plug any security vulnerabilities. The hacker reappeared in the afternoon, this time visibly taking over the computer and opening the plant's control system software. The intruder departed after increasing the water's sodium hydroxide level from 100 parts per million to 1,100 parts per million. There's little formal visibility into the number of attacks on water utilities. Many go undetected or unreported, as there's no federal law requiring any regulatory notification or law enforcement disclosure. There was legislation in 2018, but Congress never appropriated the necessary funds. Water utilities perform self-assessments. However, if there's disagreement amongst professionals, cyber self-assessment might not resolve the cybersecurity problems. Here we look at the use case for PROTECT. The genesis of the operational requirements is from the DoD Advanced Cyber Industrial Control Systems, Tactic, Techniques, and Procedures, and the Mosaics Joint Capability Technology Demonstration. Questions formulated for the test tool on the right show how the questions of our tool mapped to operational requirements. Please take a look at the first row regarding access control and user accounts and credentials. Then realize there are more than 148,000 public water systems in the United States. Virtually all rely on remote access to monitor and administer facilities. Most operations are unattended and operate 24/7. Most have not separated IT from control system functions, such as the safety systems. US water infrastructure lacks centralization, so a widespread water hack would be challenging as each facility runs independently. But rural areas in particular often get their water from small plants, which are often run by a handful of employees rather than dedicated cybersecurity experts. In most cases, it's up to individual water plants to protect themselves, even if they are aware if they've been hacked. More than 80% of surveyed facilities recently declared they had significant vulnerabilities, such as software flaws that included in Oldsmar that was discovered before 2017, indicating that there's a rampant problem of employees not updating their software. So let's talk about the Oldsmar, Florida water treatment facility. A best practice is to protect the network by protecting remote access, virtual private network, protecting wireless access points, and using strong passwords to protect against unauthorized access to the physical system. One of the ways that the Mosaics JCTD brought, a capability that the Mosaics JCTD brought to the realm of cybersecurity for control systems is that it provides an automated response action following the ACI TTPs. So some of the things that an individual might not be an expert at, this tool would be able to, or the suite would be able to provide a course of action that was predetermined to support if there were any changes or attempted changes to the system. In the system, we see remote operations, assistance, and alarms. To the left, we see the Mqtt, which is a machine-to-machine connectivity protocol used for the Internet of Things. It's a lightweight publish, subscribe messaging protocol, which makes it one of the more suitable for various IoT devices. We see the IoT, or the Internet of Things, uses the Mqtt to publish the device activations and messages that enable the publishing of a message for a specific device response. The primary application use cases are remote operations, remote assistance, remote alarming. Two technical use cases are monitoring to make any data processed on a device available, and it helps the user understand what is going on in their control system network. Here we see in figure 15 comparing engineers with computer scientists in like manner about infrastructure, and we see a high R valued. Thus an R squared of 0.7495 for engineers and computer scientists is high. However, we also see that the agreement with technicians about infrastructure has an R squared of 0.061 as shown in figure 16. Participants were asked questions about infrastructure and were also asked questions that related, such as, I know the single points of failure, which is shown as 0.2932 in figure 15 and is 0.832 in figure 16. So you can see that there is a disagreement that's leading to misalignment to vulnerability. So for example, administrative password use on multiple systems, a shared password, VPN accounts that would enable someone with stolen credentials to access a system, that leads to a vulnerability of compromised credentials that enable a nefarious hacker to access the system. We can walk that back through the model as well and look at, well, we have software flaws. The alignment would be purchasing updated operating systems and leading to an agreement of performing regular software updates and credential management. Participants were also asked questions about red team activities, such as red team recommendations are tracked to resolution as part of the risk process, which you see here is 0.145 in figure 17, and red teams meet current mission requests made by our organization, shown as 0.1411 in figure 17. So that shows the correlation between energy and financial services about the red team in figure 17. Energy with financial services about red team has an R squared value that is weak of 0.0809. So that shows that there is a, for the facilities, that there is a moderate correlation for the data set. Red teams would benefit by sharing their knowledge with commercial sectors, and red teams may understand where vulnerabilities might be. It's a very reactive response. For example, if a red team is spending the whole time preparing for an exercise, assuming that there'll be a network launch to solve, and the red team is spending the entire time, or if the blue team is spending the entire time preparing for an exercise, assuming there's a network launch to solve, and the red team is spending the entire time working on an insider threat strategy, the team will be proof against something that this team is not doing, and this team will be trying to be doing a penetration with something for which the other team has not prepared. So that means the whole exercise is essentially meaningless. So great, you can attack something that's not been defended and defend something that's not been attacked unless they're on the same page and understand the vulnerabilities. Where the correlation is very poor, these professionals will be at competing odds, which is worse than not fixing the infrastructure. Well, parts of the organization fixing the infrastructure, competing against each other for resources or what the approach is. So imagine if we right now we're trying to build a bridge or to build this infrastructure, and instead of having a plan, we have two teams that just start building, and both building from their respective ends of a bridge. They come together completely mismatched because they did not create an overall design. They did not work with one another. And this is what's going to happen with cybersecurity and control systems if we're not careful. We'll have people who believe A is okay and are working towards B, and others who believe B is okay and they're working towards A. And when they come together, their two roadways are not going to meet. That both ends will drive us into the water. So the result is many useless infrastructures that did not create a cohesive whole. The value of null findings in the uncertainty model is equally important. I'd like to highlight that. I'm not suggesting that everyone must be in groupthink mode. More significantly, the null findings of research can also indicate that or challenge the claim that cybersecurity specific training alone improves cyber fluency in control system operations. Two examples of weak voices of departure from a concurrence of agreement that proved deadly are the Apollo 1 launch pad capsule fire and the Challenger space shuttle explosion. In 1967, our 3 astronauts died in a flash fire inside their Apollo 1 command module during what was supposed to have been a routine simulated launch test at Cape Canaveral, Florida. Astronauts Grissom, White, and Chaffee voiced concerns about the command module earlier, citing the number of flammable materials used in the model. And despite the astronauts' concerns, the combined nylon and Velcro materials that were used to hold the module's tools and equipment in place were never removed. Later, NASA flight director Gene Kranz said, "We were just too gung-ho about the schedule and we blocked out all the problems we saw each day in our work. Every part of the program was in trouble and so were we." So evidence for the cause of this Challenger space shuttle explosion that killed its 7 astronauts in 1986 showed that a rubber O-ring seal failed to seal correctly at launch due to below freezing temperatures that impacted the integrity of the O-ring material. In addition, there was a second wind shear condition further damaging the seal 37 seconds into flight. At this point, the result was catastrophic. Like concerns voiced before the test event about Apollo 1 command module, contractors working on the Challenger space shuttle booster rocket expressed safety concerns about the forecast temperatures on the planned launch day. So one of the important things about understanding the disagreement that leads to misalignment, that leads to vulnerability, is that sometimes we also have to have those measures of disagreement and understand why engineers and computer scientists might be thinking one way and why safety and technicians on a control system might be thinking another way. Extension of connectivity and the digital transformation of engineering to critical infrastructure introduces new systems engineering challenges. Implementing policy or adding new capabilities to defend control systems will not work if there's disagreement amongst professionals. So while the government is trying to bring together key elements, a genuine concern is that throwing money at this problem is not resolving vulnerabilities until stakeholders agree on the resources. Despite all the valiant effort, there'll continue to be increased vulnerability if disagreement and misalignment on what constitutes cybersecurity vulnerability are not addressed. It's worrisome when there are competing views between professionals. When data shows no correlation between two professionals, that is a vulnerability. When that vulnerability is identified, future research can lead to resources allocated given known disparities between how professionals think a control system's cybersecurity is functioning. The professionals will be competing against each other otherwise, and worse, undermine the work that's been done to actually secure the system. Shared understanding is needed, or will not build a design from the ground up to address cybersecurity, let alone retrofit security into a system. Professionals will be working from different assumptions and will not be able to come together. The process presented today is a new means of addressing uncertainty using measurable data that otherwise ends up in vulnerability. The result of the research will contribute to the systems engineering body of knowledge to achieve by measurable statistical difference and maintain command and control over the cyber-physical system or control system domain without uncertainty. The approach is new, an innovative model, and a novel methodology, and the output from this model leads us to identify specific areas of vulnerability that can then be resolved. So I'm showing that the relative ranking and the relative concern that people have with things differ, and the order they have it in can be rolled into a cyber R² value, which shows that they have different priorities. If they have different orders, they have different priorities. If they have different priorities, they have different things that they think are the real concern, and that is disagreement, which is a misalignment in terms of what they're going to try to fix, which is a vulnerability. There are all kinds of vulnerabilities, but those vulnerabilities will be a lot easier to address and a lot more cost sensitive to address if we agree with what we're trying to do. So thank you for listening to my presentation. I greatly appreciate and value your time, and I see, or I can't see, I see that there might be some questions in the chat, so I'll have to stop my share here and look at the chat.
I think there is some, thank you, Ms. Scalco. A lot of ground you covered and really interesting. I don't think there's any questions in the chat that I identified. There's some conversation about some administrative stuff in there, but I don't think, if anybody has questions, feel free to unmute yourself and just ask a question.
I really appreciate everybody hanging so late and staying for an hour presentation. So thank you for sharing your time and energy. Really appreciate that.
Hey, I think I have a question.
All right.
This model, you say, is very novel, right? This is the first time something like this has been applied to, well, right now, primarily you were, focused on control systems application, but it seemed also, it could apply to other types of technologies and technology development professions and stuff. Am I gathering, is that correct? Right?
Yeah, that sure is. It would be really interesting to bring in other types of similar surveys that could really be on any type of subject and run it through the model to see where there's disagreement that leads to misalignment, which leads to a vulnerability,
Right.
and walk it backwards through the model as well. So you're able to go one way and then back through the model. So it wasn't just the survey tool itself, it's actually that analytic model of how you're able to walk through to the vulnerability as well as back through the model. And then you're able to put your finger on, oh, wow, here that we have a misalignment that is backed by quantitative data. So there's likely going to be a problem. Now, what the solution is that you look for, is it an automated solution? Is it policy? Is it more training? Whatever it is, but you have that quantitative data now that you're able to walk backwards and forwards through the model. Yeah,
yeah,
and
that's
other fields.
Yeah, that was actually going to be like a sort of follow-up question, because one of the things I was thinking while you were talking through all this is like, whoa, now we know what the problem is, but how do we fix it? That's also a tough question, right?
Yeah, so I'm really excited about future directions for this research, and am looking forward to continuing to see how we can apply this particular model to other types of work as we're looking at developing capabilities, staying focused on cybersecurity, for example, and really building out that model and demonstrating it or testing it on other programs. Great, let's make it more robust. But there are a lot of directions we can go. I think on one of the slides you saw where I had kind of a model-based systems engineering and being able to really visualize, hey, look, here's where you're developing a system, and here are the folks that it's for, and they're on the opposite ends of the Q-tip, right? So there's likely going to be some challenges in the transition. And particularly when we look at the Department of Defense, all of the fantastic early research and development that we're doing on building secure systems, whether it's a secure system, and being able to fill it, we have multiple valleys of death where that handoff occurs. Well, if you have group A that's trying to hand off a solution to group B, and group B thinks that group A is in bad shape, and group A that's trying to pass it off to where we're trying to field a system thinks they're in bad shape, well, it's going to be really challenging to go across that valley of death.
Thank you. I think we do have one question in the chat room here, Raul Vidal. You see that?
A moment. How do you weigh the disagreement? Can you clarify what you're asking about weighing the disagreement? Do you mean what is the formula, like taking
I'm
a
sorry.
set of questions
I'm
and
coming in now. This is Roll. So, I don't know if you can hear me. If my internet is not so good, I apologize for that.
that's all right. That's all right.
So, good night. Yeah, it's great presentation start. But like when you're doing statistics and I see correlations and you see some are, when you identify the disagreement, I guess the weight, like the cost function or weighting, like the impact of the disagreement, that will impact your correlation and everything that you build on it. So when you find a disagreement, I don't know if I missed it, and you spoke, I apologize. So like you can have like mild disagreement, and it's the impact between those disagreement is not as critical as a different disagreement in the same system. So I was kind of trying to find when you come together, you sit down, you analyze how does that look like, because a mechanical engineer sits down with a systems engineer and we have a disagreement, but how you assess the weight of that disagreement in per se is surveying. So that's where.
Yeah, okay, so I understand where you're coming from. So, okay, we were looking at the entropy and the cove that was ranked, and then we summed it for the overall rank of uncertainty, and that's what you see in the scatter chart. And I think one of the things that you're asking is, using the Likert scale, we gave the responses a score. So yes, 1, no, 2, and I don't know, 3, so that a higher score reflects a higher level of uncertainty for each item. Right? So we have the Likert entropy, or the LE, and the coefficient of variation. And I think another aspect of your question, if I understand correctly, is you're asking about the impact of what would be the most important. So if we looked at the sets of questions, we had network systems, infrastructure, incident response, resources, training, knowledge, skills, and abilities, red team, and security considerations. So I think part of what the question that you're asking is, you could take the survey, you could look at one specific area in the same way we do in program and project management. Okay, pick one and we're going to concentrate on network systems, or we'll concentrate on resources, training, knowledge, skills, and abilities. So you can prioritize in that way based on what you're looking for to address, and perhaps tackle them by section of section. But in terms of impactful, is it more important if your network systems fail, or if your infrastructure fails, or if security considerations? I think that aspect is up to the organization that is using the tool to measure the model on what they want to target. And then when you take those, the R² scores that shows the values, that's really when you can start looking and saying, okay, which one of those are we going to prioritize and tackle? But ultimately, when you have two parties that are just completely opposite of agreeing, then there's going to be a challenge. So if there's no agreement on knowledge about facilities and infrastructure that are used in operations, then the likelihood of there being a disconnect that is greater than the vulnerability that's innately designed in the system is going to be high. Did that make sense? I'll take that as a yeah for now, but we can take offline. I'm always excited
There
as
you go.
you can tell to talk about it. But I see
I
that
think he had
there.
his mic muted or something. Okay.
Yeah. Can you describe the process you used to generate the questions, and were the questions developed by subject matter experts or derived from government artifacts? Well, to generate those questions, that was, again, phenomenal coursework at Colorado State University. Spent the last couple of years in courses led by, like Professor Steve Simsky, who's also my advisor. He taught a course on cybersecurity. So during that course was really when we started evolving and trying to figure out what to ask. So no, they were not derived from government artifacts. They were really derived from, as we were going through the cybersecurity class, and in parallel, I was working as transition management for NAVFAC, and really starting to think about what kind of questions do I have, or what kind of questions, through the course that we're taking. Interestingly, we came up with a lot of questions and a lot more questions. If I had it to do over again, perhaps suggesting or asking participants to answer 203 questions might be a bit much. It can maybe be broken into other chunks, but we had a good response rate. So hope that answers your questions, as we just really started chunking through what kind of questions we had as subject matter experts ourselves on cybersecurity. And Scooby-Dooby-Doo, Catherine Collins, thank you. You're welcome. Thank you for saying thank you. Miscommunication, understanding of first. Yeah. It is really important, that first step. And one of the things that I'm seeing is it's very challenging, particularly in the DoD. We are very, we have limited resources, and we have to be very judicious about where those resources are applied. So I think that this tool, being able to walk through from disagreement through to vulnerability and backwards, will help us to really start identifying where we can look at what are some science and technology capabilities, or where are some of the gaps, and really help navigate that through the .mlpfp process to help identify where to put those resources. Yeah. Any other questions?
Okay, this is Marquez Merrick. Really like this. Is very good, very enjoyable.
Thank you. Nervous for what follows that. Yeah.
Yeah, but when I look at this, I'm like, oh my God, because when I see, when you started showing those plots, I think they were grouped by 9 or something, 6 or 9.
Yeah.
And you had, and I thought, well, wait a minute, there's only like one block there that's at most showing a good correlation. So that kind of scares me that there's if you stack them all up and put them on one page and said, okay, we're going to group all the ones that are strong, you maybe get 10, and you get 95, others that are, medium or totally weak. And I'm like, there's got to be other threads in there. You should be able to, finally analyze and say, okay, maybe focus on that one segment and just try to determine, okay, what is really bad here, and where we're going. Because I think the thing is too, is with designing again, if you're trying to design something new, getting a lot of the stakeholders in the room all at the same time, so to speak, to talk it out somewhat, but that doesn't always happen. And when you were looking at the things with the water system, that was like, well, yeah, some of these systems are 30, 40 years old, and a lot of this stuff wasn't even considered. And like you said, they're still maybe running Windows 7 or something like that. I mean, it's just, it's very scary. So
it is.
Yeah.
It is.
I mean, now granted, some things can be worked around, either upgraded equipment, but then again, easiest is, like you said, strong passwords and VPNs installed, et cetera, some simpler items that can be done, fairly quickly. But that just,
But agreed upon, right? So
yeah.
I really value and thank you very much for seeing the value in this model and this methodology and the approach of being able to walk back and forth. Because if you pay attention to the voices that we're hearing, we'll hear like the legislation in 2018 to secure control system facilities, and the funds were never appropriated. So there were no funds for that. Or then even that for systems that under a certain number of customers were exempt because of recognition that they don't have the resources. But at some point there has to be some agreement, which is how much money are we going to be throwing after a problem if we have reuse or shared passwords, which, why don't we have a system that comes out of the box that, every 30 day, or if there is an application on a system, every 30 days, a system admin has to concur that there is a use for it, or it's flushed from the system, or something comes out of the box and you have to change the password. You can't reuse a chat. So there are, I mean, but that requires agreement and alignment, right? So, but recognizing that we have a problem, then there's hope, right? And as systems engineers through Incose, now we have hope. We're going, wait a minute, we're systems engineers, and we're saying these engineers and competencies are telling us one thing, and these engineers and other competencies are telling us another thing. So as systems engineers, where we have the greatest influence, right, is bringing together those competencies so that the two systems understand what the value is in each of their voices, and that we're able to deliver something that works.
Yeah, well, I think you waved this set of slides in front of them if you get the chance. And I think that will open their eyes pretty much. Yeah, this is, you know, again, I'm just kind of scared now. I mean, I look at it and go, oh my God, this is, you know, I mean, you're very sophisticated with your findings in the model, but it's scary when you look at the results and say, you know, well, no wonder why so many things seem to be hiccuping and having issues in the cyber world. So,
yeah. And one other thing that you said that kind of brings up is as we look at these systems and identify where we need to put resources to, it's the understanding that there is a misalignment is just absolutely so key for us to be able to address it. But then also when we look at where the funding is going to, right? It's like, what are we trying to address? And one of the things that really triggered, that kind of started the path of this research was I was constantly hearing, I don't know if you hear, we need to do more cybersecurity training of cybersecurity experts because that's going to secure our systems. Well, based on this quantitative data, and we have quantitative, so it's not an opinion. When I did this research, I think something like 98% plus had cybersecurity training. And that included everybody. So 98% have cybersecurity training, and yet two ends of a Q-tip, completely not in alignment. So, and the other thing about this particular survey, so I'd really look forward to future research and others participating and making it more robust, is those that were willing, when we were first putting out using this as a tool, as a launching point, were people who had vested interest in cybersecurity for control systems. So I hope that there wasn't just someone kind of going, hey, I want to spend my half an hour taking 203 questions. These were subject matter experts, cybersecurity training. So I don't know that throwing more money after training is the right answer, but we'll see where research takes us.
Okay, well, I hope it works out, and let us know.
Okay, it's 1:15. Let me thank you first, and then we'll give away the door prize, and then I'll leave the room open for a little bit longer if there's some burning questions left. But first, I want to see if I can do this. Whoops, wrong one. No, that's the Wheel of Fortune. I don't want that. I want this one. All right. This is our virtual thank you presentation, and I also want to just personally thank you for giving us such a nice, pleasant talk and discussion this evening.
Thank you.
So thank you for that. Now I will switch this to the Incose Wheel of Fortune, and we will see who will be the winner tonight. I'll spin the wheel. And it looks like Catherine Collins. Congratulations, Catherine. I'm going to use the email that you registered with to contact you, and I'll send you a copy of the book.
That's because she asked good questions.
Was that it?
Yeah, well, she was one of the, she questioned.
Oh, yeah. Oh, but I mean, that gives you extra luck, you're saying?
Yeah, there you go.
You ask good questions, you get more luck. That's it. All right, do we have anything else? Others folks asking questions? Thank you, everyone, for showing up. Appreciate it. And look for upcoming events, as always.
Oh, okay. Looks like Alexandra answered Michael Enoch had asked the question there about 2-3 minutes
Okay.
ago.
So actually, I saw Michael, your question, just to let everyone know, he has asked if I was aware of anyone using this process during requirements generation. I'll have to say, this is really the first time I've presented it outside of my Colorado State University environment. So no, would love to see that. Would absolutely love to see us build on this research. So thank you for asking.
You heard it here first.
That's right. Incose Chesapeake
Yeah.
chapter. You guys rock. Really value. Thank you so much for giving me these opportunities to
Welcome.
share some ideas. Really appreciate it. All right.
All right, folks, if there's nothing else, then have a pleasant evening.
All right. Thanks.
Yep. Good night, all.
Good night.
All right, great job. We'll see you.
Thanks.